This is another conservation of energy question, but it's got a little bit of a twist to it, which is why I chose this example. Let me draw the picture for you, and then we'll have a look at what the case is. So we have an electron, so we know we got some parts to the electron. It's placed between two parallel plates that are 8 centimeters apart. So let's just draw two plates, 8 centimeters apart. The potential difference between the plates, well, first of all, let's jot a few things down here. The mass of an electron is 9.11 times 10 to the negative 31 kilograms. The charge on an electron is negative 1.60 times 10 to the negative 19 coulombs off your data sheet. The distance between the plates is 8.0 centimeters. The voltage between the plates is 55.0 volts. What we want to do is figure out how much work, so we're looking for how much energy is done if the electron is moved 2 centimeters perpendicular to the plates. So I'm going to stick my little electron in here, and I'm going to move it perpendicular to the plates 2 centimeters. Now it doesn't matter on your picture whether you draw this thing up or whether you draw this down. It's irrelevant because it just has to move perpendicular. We're looking for a change in energy. It doesn't say how much is converted to kinetic, how much is converted to potential, because we don't really know what the charge of each plate was. If the bottom plate's positive, then it's gaining kinetic energy. But if the bottom plate was negative, then we're gaining potential energy. Doesn't matter. It's just saying how much work is done, period. Now here's the trick. The 55 volts is how much energy the electron would gain if it moved the whole way. Well, it doesn't move the whole way. It doesn't go from one plate to the other like example 2 did. This is only going a distance between these two. So you have to be very careful when you punch this in on your calculator. You could find out what the total energy would be for the full 8 centimeters and then find out how much it would be for only going 2 centimeters. There's lots of ways to do this question, but it doesn't get the full 55 volts. The only way an electron would get the full 55 volts is if it went from one plate all the way to the other. Would you get that much change in energy? So that's one thing we got to be a little bit careful about. So what we want to do is we want to know how much work is done if the electron moves 2 centimeters perpendicular to the plate. Well, we have this formula. Change in voltage equals change in energy over Q. What we want to do is we want to find out how much energy. It's equal to Q change in V. But we have to remember how much voltage is really being acquired here. So we can work out what the total would be if it went for the full 55 volts. So you get 1.60 times 10 to the negative 19 coulombs times 55 volts. And there's lots of ways to do this question, by the way. So 1.6 to the exponent negative 19 times 55 gives you 8.8 times 10 to the negative 18 joules. So it's just like if you dropped a book the full way, it's going to change the entire energy from top to bottom. But same thing in this case, because it doesn't go the full way, we don't get the full change in energy. So there's really a ratio between the distance it actually travels to the distance it actually is between these two objects. Just like if you dropped a book and it only falls 2 centimeters out of the entire 8, it doesn't have the full change in energy. That's what I'm trying to say with this as well. So if you were to think of the ratio between those distances, then what you could do is multiply the total energy by that ratio. Another thing students do is they figure out the ratio of those distances and multiply the voltage by that ratio. So that the students go, well, it didn't get the full 55, it got 2/8 of that full 55. So this thing really does travel 2/8 of this. So I'm going to write this as it actually travels 2.0 centimeters out of the total 8.0 centimeters. That's how I kind of set these up and realized that it didn't get the full energy change from one plate to another. It has a ratio of this. And if you take that number, 8.8 times 10 to the negative 18 times 2 divided by 8, you should get the total energy change in this case as being 2.2 times 10 to the negative 18 joules, which is less, which should make sense because it didn't get the full voltage from one plate to another. So you have to be very careful with these when you're given it only moving partial distance. You need to find that ratio because it's not the full voltage it acquires from one end to the other. It's only acquiring some of that voltage. Just like when you drop an object and you stop it somewhere along the way, you only have some of its energy change. Same thing here. This is a very, very common type of diploma question, and the really tricky thing is the diploma answers will have the 2.2 times 10 to the negative 18 as one of the choices, but they also give that 8.8 times 10 to the negative 18 as another choice. And it always fools about 60% of the students because they forget it's not going from one plate to the other, it's only going a little bit of distance in between. And that's why I threw this example in. It's very similar to example 2, but example 2 went from one plate to the other. If you have a ratio, multiply that energy by that ratio. This should complete our unit. So what you're going to do is, if you have a look in the WebCT schedule, there's a bunch of questions that you could do for review. I've got them already in your notes. And get ready for the self-test, or get ready for the exam by practicing the self-test, and get ready for the exam.